Hello everyone, my name is Laetitia Marot. I am a researcher at InnoRenew, and I will present you a preliminary study initiated with Fraunhofer on the use of agrocomposite for the reinforcement of concrete. Concrete is by nature resistant to compression, but is weak in tension. The conventional way to reinforce concrete is to use steel bars, but this reinforcement is heavy and sensitive to corrosion. Another way to reinforce concrete is to use a textile that can be made of various materials. So here, for example, you have a textile made of glass fibers, which has inert properties. So the cross-section can be much thinner than for the conventional concrete, and it reduces carbon footprint and cost. The goal of the study is to investigate the suitability of a textile made of plant-based fibers as a sustainable reinforcement of cementitious pieces. Among the plant-based fibers, the flax fibers are biodegradable, renewable, and show the best tensile properties with alpha and rami fibers. We chose to work with two different flax fibers textile. The flax one that you can see on the left is a woven fabric, and the flax 2 is a grid that you can see on the right. They have both the same grammage, around 200 grams per square meter. We characterize them by a tensile test, and the force strain curves show that there is a first part corresponding to the load of the flax fibers before they are pulled together and really play their reinforcement role. This happens around 2.5% for flax 1 and 1% for flax 2. It actually corresponds to 5 and 2 mm strain respectively. The concrete, when it hardens, generates chemical products that create a very alkaline environment, so the reinforcement needs to be alkaline resistant, not to be damaged. Flax fibers are decomposed in alkaline environments, so we used bio-based coating to protect the fabrics. And then we assessed the coatings by immersing the fabrics for 1 month at pH higher than 13. We measured the rate percentage of mass loss, which we want as low as possible, and we can notice two things. First, when uncoated, the flax 2 has a lower rate percentage of mass loss than the flax 1. So not all the textile made of flax fibers are similar regarding the alkaline resistance. 2. The bio-based alginate coating can be interesting because for the same rate percentage of mass loss, the coating will be damaged before the reinforcement. We can also notice that the epoxy coatings brings improvement for this property. The tensile capacity retention rate gives the residual tensile force after the test, but the experiments are still in progress. We manufacture textile reinforced concrete with the textile 1 using 3 to 5 layers, and we tested them after 28 days by the 3-point bending test. The experimental results give the flexural strength and the flexural modulus higher for the knit concrete than for the concrete with flax fibers. So flax fibers here do not play their role as reinforcement. We identified at least two issues with the experimental settings. The first one is that the tensile strain of the concrete is very low, so the flax reinforcements are not loaded yet when the samples break at about 1 mm of displacement. So one solution is to impose a pretension of the fabrics during the manufacture of the textile reinforced concrete. The second issue is the grain of the concrete that is quite coarse, and the opening of the flax 1 fabric is too small for the cement particles to penetrate the spaces and to create a good anchorage between the fabrics and the concrete, so the load transfer is here limited. To conclude, we found the bio-based alginate coating to be promising. Some spectroscopy analysis will help to identify the components that are removed by the alkali test. The experimental settings for the manufacturing of the textile reinforced concrete need to be improved by using pretension of the textile and either using concrete with finer grain or a more open fabrics like the Flax 2 grid. Thank you for your attention, and I would be happy to answer your questions.